Welcome to this session on ISO 26262 with model-based design, a hands-on Simulink tutorial with an X-by-wire example. In this session, we'll explore functional safety concept outlined in Part 3 of the concept phase, and the technical safety concept in Part 4 of the product development at the system level, using a brake-by-wire system as our example throughout the discussion. Here's the ISO 26262 Safety Framework, which provides a structured approach to developing safety-critical automotive systems. It begins with the hazard analysis and risk assessment, where potential hazards are identified, classified, and used to define safety goals. Based on these goals, the functional safety concept specifies what safety functions are needed to achieve them, while the technical safety concept defines how these functions are implemented in hardware and software. The framework also includes the development of a safety architecture, which organizes system elements to meet safety requirements, and a comprehensive verification and validation plan to ensure that all safety objectives are met throughout the development lifecycle. Here's an example of a safety goal. The brake-by-wire system shall prevent unintended braking. From this high-level safety goal, several functional safety requirements are derived to ensure the system behaves safely under fault conditions. These include implementing fault detection and isolation to identify and contain failures, enforcing timing constraints to maintain real-time responsiveness, defining a safe state, such as controlled braking or pressure release, in case of faults, and providing monitoring and warning mechanisms to alert the driver or higher-level systems. We then move on to derive the technical safety requirements from the functional safety requirements. These technical safety requirements define how each safety function will be realized through specific hardware and software implementations. For example, fault detection and isolation may translate into hardware redundancy, diagnostic monitoring circuits, or software-based plausibility checks. Timing requirements might be addressed through real-time operating system scheduling or watchdog timers, while safe state management could involve hardware interlocks or fail-safe control logic. Monitoring and warning functions are implemented through sensor diagnostics and communication interfaces. Together, these technical safety requirements bridge the gap between the functional safety concept, what needs to be done, and the system architecture, how it will be achieved, forming the foundation for design, verification, and validation activities. The safety concept should include at least the following key elements to ensure a comprehensive and compliant safety design. It defines fault detection strategies to identify potential failures and degradation mechanisms to maintain limited functionality under fault conditions. A clearly defined safe state specifies how the system behaves to prevent hazards when faults occur. Timing requirements ensure safety functions respond within acceptable time limits, while driver alerts communicate warnings or required actions to the user. The concept also details safety mechanisms, both hardware and software, that achieve or support fault tolerance. Furthermore, it includes requirement allocation across system, hardware, and software levels, ASIL Decomposition to distribute safety integrity levels appropriately, and a defined verification method to confirm that each safety requirement is correctly implemented and validated throughout the development process. Let's begin with the safety mechanism. We will then discuss the safety mechanisms implemented across different levels of the system, including the system, sensor, actuator, electronic control unit, and software. At the system level, safety mechanisms are implemented to guarantee robust fault containment, effective redundancy management, and controlled transitions to predefined safe states. These measures ensure that any detected fault remains isolated, prevent cascading failures across subsystems, and maintain operational integrity by shifting the system into a safe configuration when necessary. At the sensor level, safety mechanisms incorporate multiple strategies such as plausibility checks to validate the consistency of sensor readings, continuous signal range monitoring to ensure values remain within expected thresholds, and built-in redundancy to provide backup measurements. These measures work together to detect potential failures, signal degradation, or gradual drift over time, thereby maintaining data integrity and supporting reliable system performance. At the actuator level, safety mechanisms incorporate multiple layers of protection, including continuous feedback monitoring to verify that the actuator responds accurately to control commands, current sensing to detect abnormal electrical conditions such as overloads or short circuits, and fault-tolerant drive circuits designed to maintain functionality even in the presence of certain failures. Within the ECU, safety is reinforced through several critical mechanisms, including power supply supervision to maintain stable voltage levels and prevent unexpected shutdowns, watchdog timers that continuously monitor software execution to detect and recover from system hangs, memory protection techniques that safeguard against corruption or unauthorized access, and diagnostic communication protocols that enable real-time fault reporting and system health monitoring. Finally, software-level mechanisms such as task monitoring, data consistency checks, and graceful degradation strategies provide an additional layer of protection. Together, these mechanisms form a robust safety architecture that helps the system detect, handle, and recover from faults effectively. Please feel free to pause here and take a moment to review these examples of safety mechanisms. Building on the discussion of safety mechanisms, here is a high-level implementation of the system architecture in Simulink. The model includes two dissimilar pedal position sensors to provide redundant and diverse input measurements, and two control channels within the brake control unit, each comprising a command module and a monitor module. A voter component is integrated to compare the outputs from both channels and determine which command should be active, ensuring fault detection, redundancy management, and reliable system operation in alignment with the safety concept. All right, let's move on to system degradation. A degraded mode strategy defines how a system continues to operate safely when faults occur, balancing functionality and safety. In a fail-safe approach, the system transitions to a state that eliminates or minimizes hazards, such as disabling automatic braking or reducing torque output, to protect the user and vehicle. A degraded mode allows partial or reduced functionality while maintaining essential safety functions, for example, operating with a single sensor or limited control channel. In contrast, a fail operational strategy ensures the system continues to perform its intended function, even after certain faults, often through redundancy or fault-tolerant design. Together, these strategies ensure that regardless of the fault severity, the system maintains safety, transparency, and predictable behavior throughout its operation. Here's a high-level stateflow implementation that visually represents the system's various operating modes, including normal operation, degraded states, and safe states. It also illustrates the specific conditions, events, and logical checks that trigger transitions between these modes, providing a clear overview of how the system responds to faults, recovers from errors, and ensures safety under different scenarios. Here are examples of system architectures illustrating the difference between a fail-safe system and a fail operational system. The fail-safe architecture is designed to transition the system into a safe state when a fault is detected, prioritizing safety over functionality. In contrast, the fail operational architecture incorporates redundancy and fault-tolerant components, allowing the system to continue performing its intended function even after certain faults occur, ensuring continuous and reliable operation. To detect faults, diagnostic is requested. And diagnostic coverage is a key metric in functional safety that measures the effectiveness of a system's fault detection mechanisms. It measures how effectively a system detects and handles faults through mechanisms like monitoring, plausibility checks, and redundancy. Higher coverage reduces the risk of undetected failures and supports compliance with the required ASIL level in ISO 26262. It's typically validated through fault injection, testing, and simulation to ensure the robustness of the safety concept. Okay, let's move on to safe state. A safe state is a system condition in which hazards are avoided even if normal operation cannot continue. In brake-by-wire system, The safe state must ensure that the vehicle does not apply unintended braking, and the driver can still bring the vehicle to a controlled stop. The safe state depends on the fault severity and system design: fail-safe, degraded, or fail operational. Here are some examples of safe states. Please feel free to pause here and take a moment to review them. All right, let's move on to timing. The timing of safety mechanisms is crucial to ensure that hazardous events are avoided when a fault occurs. When a fault occurs, it may not be detected immediately. The Diagnostic Test Time Interval, DTTI, is the maximum time allowed for the system to detect the fault through diagnostics. Once the fault is detected, the system enters the Fault Reaction Time Interval, FRTI, during which it must react and transition to a safe state before a hazardous event can occur. The sum of the DTTI and FRTI is known as the Fault Tolerant Time Interval, FTTI, which is the maximum permissible time from fault occurrence to the transition to a safe state. If the system transitions to a safe state within the FTTI, a hazardous event is avoided. If not, a hazardous event may occur, potentially leading to harm. Therefore, the design must ensure that detection and reaction times are sufficiently short to prevent hazards, with the safe state tailored to the system and fault severity. In a brake-by-wire system, a fault, such as a loss of braking, can lead to hazardous situations. Upon detecting such a fault, the system must trigger a warning to alert the driver. The driver should then attempt to bring the vehicle to a safe stop. Okay, let's move on to verification methods. In ISO 26262 compliant development, Model in the Loop, MIL, verifies control algorithms and functional requirements early using executable models. Software in the Loop, SIL, tests automatically generated code in simulation to ensure it matches model behavior. Processor in the Loop, PIL, runs the code on the actual processor to validate timing and numerical effects. And hardware in the Loop, HIL, connects the real ECU to a real-time simulator to verify closed-loop performance under realistic conditions, all ensuring safety, consistency, and correctness from model to hardware. In addition to these 4 verification methods, which focus on verifying functionality and implementation throughout the development process, Failure Modes and Effects Analysis, FMEA, provides a complementary approach to evaluating system safety. FMEA systematically identifies and assesses potential failure modes, their causes, and their effects on overall system behavior. By analyzing the severity, likelihood, and detectability of failures, FMEA helps prioritize design improvements and ensure that safety goals defined by ISO 26262 are effectively met across all development stages. Here are some examples of FMEA. Please feel free to pause and review them. In summary, here are some examples showing how safety goals, safety requirements, and safety mechanisms map to corresponding verification methods. Please feel free to pause and review them. In ISO 26262, a traceability matrix ensures clear and consistent links between all elements of the safety lifecycle, from safety goals to safety requirements, implementation elements, and in ISO 26262, a traceability matrix ensures clear and consistent links between all elements of the safety lifecycle, from safety goals to safety requirements, implementation elements, and verification methods. It provides a structured way to demonstrate that each safety goal is properly decomposed into technical and software requirements, implemented correctly in the design or code, and verified through appropriate testing or analysis methods such as MIL, SIL, PIL, HIL, or FMEA. This end-to-end traceability is essential for confirming that all safety objectives are fully addressed, no requirements are overlooked, and every verification activity directly supports the achievement of functional safety compliance. All right, let's move on to ASIL decomposition. ASIL decomposition is a concept in ISO 26262 that allows a higher automotive safety integrity level ASIL requirement to be divided into multiple redundant elements with lower ASILs, provided they are sufficiently independent and collectively achieve the original safety goal. This approach helps optimize development effort and cost by avoiding unnecessary application of the highest ASIL across the entire system, while maintaining the required level of functional safety through architectural independence and fault tolerance. For example, an ASILD safety requirement can be decomposed into two independent ASILB components, which together provide an equivalent level of risk reduction to the original ASILD requirement. In this example, the safety goal is to prevent unintended braking with an ASILD classification. The corresponding functional safety requirement, the unintended brake command shall be detected, is also assigned ASILD to optimize implementation while maintaining equivalent safety. This requirement is decomposed into two independent lower-level requirements. The brake command shall be measured using pedal sensor 1, ASILBD, and the brake command shall be measured using pedal sensor 2, ASILBD. Together, these two ASILBD channels provide sufficient redundancy and independence to achieve the original ASILD safety goal. Here are some examples of ASIL decomposition. Please feel free to take your time to review them. All right, let's wrap up. The functional safety concept defines what safety functions are required to achieve the system's safety goals, focusing on the intended behavior needed to mitigate hazards and ensure safe operation. In contrast, the technical safety concept specifies how these safety functions are implemented at the system, hardware, and software levels to fulfill the functional safety concept requirements. By applying model-based design, engineers can accelerate the development and refinement of both concepts through executable models, automated verification, and simulation-based safety analysis, enabling faster iteration, early detection of design issues, and stronger traceability from safety goals to technical implementation. Here is an example demonstrating how simulation can be used to evaluate and analyze safety mechanisms by modeling vehicles, road profiles, faults, and various scenarios. Model-based design significantly accelerates the development and iteration of safety concepts by enabling a shift-left approach, where models and simulations are used early in the development lifecycle. By creating digital representations of systems, engineers can rapidly prototype, analyze, and validate safety requirements and behaviors in a virtual environment before physical implementation. This allows for early detection of design flaws, comprehensive exploration of fault scenarios, and iterative refinement of safety mechanisms, all at a fraction of the time and cost required for hardware-based testing. Ultimately, model-based design fosters a more agile and robust process for achieving and demonstrating system safety, reducing late-stage surprises and supporting compliance with safety standards. All right, we're done with the safety concept. In the next session, we'll explore Part 6, Product Development at the Software Level. I look forward to your participation.